All right, thank you for the introduction. As Professor Keeling said, I'm Vijay Shah, and I'm going to be modeling the interface between silver and silicon nanoparticles. Nanoparticles are small materials that consist of, in the case of our simulations, an inorganic core, meaning that the material or the atoms that the core is made out of are not made out of carbon, hydrogen, etc. Rather, they're made of silicon and silver in our simulations. Each of these nanoparticles are covered in different types of chains made up of carbon, nitrogen, and hydrogen atoms. And nanoparticles have been shown to exhibit size-dependent properties, in particular optical and electrical properties. So optical properties include both photoluminescence and surface plasmon absorption. And surface plasmon absorption allows the nanoparticle dispersions to exhibit different colors when they're viewed with different types of experimental apparatuses. And for electrical properties, the organic chains covering the nanoparticles can actually hinder the conductance of the nanoparticles. And overall, there are many practical applications of nanoparticles, including to photovoltaic cells. So the objective of our research is to determine the best electron donor and best electron acceptor and use this pair in order to help facilitate the charge transfer between nanoparticles. So in particular, we will be looking at the density of states, the absorption spectrum, and partial charge density in order to characterize the charge transfer between different states of our nanoparticles. So on this slide, you can see a couple of different images for our model. So on the left-hand side, we have a silicon nanoparticle. The yellow atoms are representing the silicon atoms, and the turquoise atoms represent the carbons, and the gray atoms represent the hydrogens. On the right-hand side, you see a silver nanoparticle, where now the pink atoms represent the silver atoms, and the chains are made up of different molecules such as carbon, hydrogen, nitrogen, and oxygen. And for the purpose of our simulations, which were run in VASP, the silver and hybrid models were oxidized 5 times. So this means that from the neutral model, we actually removed 5 electrons from the model when we were running simulations on them. And this was to explore different oxidized states for our model. But for the purpose of this talk, I'm only going to be talking about the simulations where we removed 5 electrons. So here on this slide, you can see 2 more different models, one being where some of the organic chains are removed from both of the nanoparticles. And on the right-hand side, you see a large ligand connected to the silicon nanoparticle. And both of these are different morphologies than when we just consider the silicon nanoparticle and the silver nanoparticle, as well as when we take both of these models and place them in the same input file. So we are really looking at 5 different models, 2 lone nanoparticles, then both of the nanoparticles brought together, both of the nanoparticles moved closer to each other in order to model the interface between these nanoparticles, and finally where we have a long ligand attached to the silicon nanoparticle. So on this slide, there's a quick movie. It's going to be very difficult to see, but this is optimization of the silicon nanoparticle by itself. So this was run using, I think, 1,000 ionic steps in VASP in order to optimize the silicon nanoparticle. And you can see the total energy after optimization, as well as both the alpha and beta orbital band gap. So the alpha represents the band gap between, or for the red states in the density of states, whereas beta represents the filled blue states, and all of the states below 0 on the vertical axis, and then finally the Fermi energy as well. So we can see that there are some electrons in the conduction band here, and this is likely because the model was not oxidized. So further work could be done in order to actually oxidize the lone silicon nanoparticle and remove electrons from the conduction band. And we'll see a consequence of not oxidizing this model in a couple of slides. Here on this slide, this is the density of states for the silver nanoparticle. So we did oxidize this model 5 times. And you can see, again, the energy after optimization as well as alpha and beta band gaps. You can see that there are, again, electrons in the conduction band. And finally, Fermi energy as well. And on this slide, here's a model where we took both nanoparticles and put them in the same simulation and optimized the entire model at once. So we have both of the nanoparticles are being optimized at the same time, and the total energy after optimization is actually a little bit higher than the separate energies after optimization for the silicon nanoparticle and the silver nanoparticle, which signifies that the binding energy is actually positive, and therefore the two nanoparticles would want to actually repel each other when brought close together. And again, we have density of states here. You can see that there's not really a distinct difference between the valence and conduction bands in the density of states. The highest occupied states are very close to the lowest unoccupied states. So on this slide, we have a couple of different absorption spectrum, and for the first 3 plots, there's a very large peak near 0 energy, signifying that incident light would have to have a very large wavelength in order for an electron to move to a higher energy state. And then on this lower right-hand plot, you can see that there are peaks at a higher transition energy, signifying that ultraviolet light can actually excite electrons from a lower state to a higher state when these electrons absorb photons. And here on this slide, you can see a couple of charge transfer plots. So on this left-hand side, these are the charge transfer plots for the HOMO and LUMO orbitals. And then on this model on the lower left-hand side, we have the HOMO orbital is represented by pink, and the LUMO orbital is represented by gray. And on the right-hand side, we see that there is some charge transfer between HOMO -4 and LUMO +5. However, there still is not too much. So further work could be done in order to actually characterize different morphologies and different oxidations and determine where the most charge transfer will actually occur, for which models they will actually occur in. So in conclusion, we see that the density of states, absorption spectra, and partial charge density plots do not actually help in facilitating the charge transfer between states when our models have 5 electrons removed from them. And in the future, work could be done in order to determine which morphologies and oxidations will actually yield the most charge transfer between states. So with that, I would like to thank Professor Dimitri Killing, Dr. Yulan Han, Aaron Forty, and NERSC and USD Cluster for computational resources. Thank you.
Okay, well, thank you, Vijay. So there is time for a couple of questions. I have one. So what is the reason for absorption close to 0 energy, and do you see, if it is not real, what are the practical ways to remove this artifact?
Yeah, so I'll go back to the plots, right here. So the question was what the significance is of this absorption spectra looking, basically having a peak at 0, how it could be removed, and if it's real or not. So the peaks near 0, right here in the spectra, were actually a consequence of having the HOMO and LUMO states be very close to each other. So the band gap was essentially 0, which means that electrons did not need to have much energy in order to go from one state to the next state when you're trying to excite the electrons. And in order to actually combat this, one would need to oxidize the model more, or in other words, remove more electrons from the model in order to have these peaks appear at higher transition energies.
Can you go back?
Yep.
More? Yes. So probably you wanted to repeat the same verbal explanation about this figure.
Right, yeah, so here we can see, as well from this figure, you see that HOMO and LUMO are very close to each other, so the band gap's essentially 0, and the same thing actually occurs right here. So you can see that this final state that is occupied is only partially occupied, and right next to it is an unoccupied state. And similarly, in the beta orbitals, there's a partially occupied state right here around negative 7.5 electron volts. And then finally, for the silicon nanoparticle by itself, again, there's a partially occupied state in the alpha orbital. And then very close to it, you see that there's a completely unoccupied state. So those would cause the absorption spectra to have peaks at low energy.
Okay.
Did you look on the localization of HOMO-LUMO in that system? Is the HOMO-LUMO in the same system or in different quantum dots?
Yeah, so we did consider I did do a simulation where this model was actually not spin polarized.
Not this one, I mean next one.
Oh, the next one?
System, yeah, I mean two.
Yeah, so yeah, we didn't actually, I didn't actually have time to consider the original model and determine like the original HOMO and LUMO for this system. That would have been something that would have been good to compare to though.
And what is the distance between these two silver nanoparticle and silicon particle?
It's very low, I believe.
No, I mean, yeah, and the two model system, two
yeah.
pair system. I forget the exact one.
Here we go. Yeah, so are you talking about like center to center distance, surface to surface separation?
Surface to surface.
Okay. I believe that was approximately 5 angstroms. It was somewhere between 5 and 10 angstroms.
So do you think that they're supposed to have any interaction between the in that distance? Any charge transfer possibility?
Charge transfer, most likely not. But yeah, interactions like binding energy, that would be present. So binding energy would be a little bit positive or a little bit negative at that distance.
Yeah.
Okay. If there are no more questions, well, thank you, Vijay, once again. And let me invite to the stage Lyndon Johnson, whose presentation title is so long that I cannot pronounce.